All right. So welcome to the implementation session of ICFP. So our first talk will be given by Benjamin. The talk is on environment sharing analysis and caller-provided environments for higher-order languages. Benjamin, you're all set to go.
Yep. Can you hear me okay? Great. Yeah, so this is environment sharing analysis and caller-provided environments for higher order languages. This is work that I did along with my co-authors Jay Carr, John Reppy, Olin Shivers, Sky Sauce, and Byron Zhang. So I want to start the talk by going through a short program example. This program example begins by binding 5 to n, then binds a function to f, which adds n to its input, then binds another function h, which takes in a function k and applies it to 6, and then we apply h to f. When we do that, it's going to apply f to 6, and then take 6 plus 5, which gives us 11. And what I want you to note about this example is that at runtime, we have to allocate a closure for f. And since f has a free variable of n, we have to package that binding of n into the closure value. And this talk is about optimizing the space that is required for closures. And so the optimization that we'd like to perform is, can f be provided the value of n instead of having to package it? So in this example, the answer is yes, because we know where f is going to be applied when we apply k to 6, and the same binding of n equals 5 is available at that location. So in general higher order code, sometimes n is available at the call, but it's not the same binding of n, because you may have a recursive function that has multiple bindings of n live at runtime. So I can transform the function here, and what I've done is I've added n as a parameter and additionally as an argument. And now f does not have to package any environment at runtime because it has no free variables. However, by adding n as an argument to the call to k, we've added a free variable to h. And that really means we haven't actually saved a word of allocation for f. We've just moved it to h. Of course, we can do this transformation again. And now we are, once we add this extra parameter to h now, and actually give it that argument at h's call, now no closure has any free variable. And so we've eliminated all of the environment allocations for our closures. So we call transformations like this caller-provided environment, because the caller is providing the environment that the function needs to run. And this is tangentially related to lambda lifting, which many functional language compilers do nowadays, except we want to do this transformation on higher order functions. And in order to do that, we're going to need a flow analysis that gives us environment sharing information, which is answering the question, when are two variable bindings shared between two environments? In particular, we have an environment that we execute the call in, that we look up k and see what it is, and we have an environment that k packages into the closure, and we want to know what bindings are the same between those two environments. We're doing this work in the context of the 3CPS compiler, which we're trying to do a lot of flow analysis and carry lambda all the way through our backend IR, contrasting with Milton's defunctionalization approach. And on our compiler, we make a distinction between the analysis side of things, which just determines facts, and the decision phase, which actually decides which heuristics to use and which optimizations to make. So this talk, on the analysis side, I'm going to show you how you design an analysis for an environment sharing, and we have an evaluation that shows how precise and how scalable that analysis is. On the decision side, I'll show you the variety of options that you have to do the caller-provided environment transformation. And I'll also tell you how to ensure that your allocations actually decrease and that you don't just move them around. And then we all have an additional evaluation for how many allocations you can save by doing this optimization. So for the analysis, what I want to do is go back to that simple program example and walk through it in a little bit more detail. And I'll put a gray box around the current program point that's being executed. And on the left-hand side, I'll have the environment that that program point is being executed under. And on the right-hand side, I'll keep track of some additional sharing information as the program runs. So we start off by binding n to 5 and stick that in the environment. Great. Next, we need to bind this function to its closure. And we can do that just as we did in the introduction. And here we have our first piece of sharing information. So f packages up the binding n equals 5, and we also have n equals 5 available in the environment. So we say that f shares n, meaning that the binding time environment of f has the same binding for n as the value environment that f packages. And there's actually a generic rule, which is that if you have any function definition, they're allowed to package up all of the things in scope. And so by reflexivity, basically, the environment has to be the same between the binding time and the value environment. Moving on to binding h, we come up with a closure for that. And by the same rule, we know that h shares both n and f, because both of those are in scope. And in this semantics, we're going to track all things that are in scope, not just the free variables, because we want our analysis to give us as much information as possible. So originally we said f shares n because the binding environment was the same as the value environment. But actually when we step the program, the current environment where f is still available still shares n, because we've just strictly extended it with h. We haven't overridden the value of n. And so as long as you have uniqueness variables in your IR, then this is a rule that sharing is going to be preserved as you step the program. Moving on to the function call, we're going to step inside of h's closure, and the environment that it packages is going to become the new ambient environment, and then we're also going to additionally bind k to the value of f. And the first thing that I want you to notice before we do that is that sharing is transitive. So f's value shares the binding of n, so the closure has an environment, there's this ambient environment, and then h's closure has an environment. And so because both f and h share n with the ambient environment, those closure values share n with each other. And what that means is that when h's closures environment becomes the ambient environment, and when we bind k to this other closure value, we know that k actually shares n. And so this is our fourth rule, which is that sharing can be pushed through calls when you have this transitivity, when you can derive it. And then of course, once we get to k applied to 6, then we know that k has the same binding of n as what's available in the ambient environment, so we can provide n at the call instead of packaging up into k's closure. So what I just went through was sort of the semantics of the program, small stepping through it. And what I additionally had was this bit on the right for sharing information. So mathematically, we have this collecting semantics where we step the program and also maintain this information on the side, like this. And in order to maintain that sharing information, we're just playing by the 4 rules that I set out on the previous slide. And I want to note that this sharing information is going to be valid for all visited states. And that's because if we have in one state that f shares n, and in another state that f does not share n, then we can't actually do the color provided environment transformation. F always has to share n in order for our optimization to hold. So therefore, when we update our sharing information, we're going to intersect as we step the program. And we have a soundness result that we formalized in Rock, which is that in this table that you're keeping track of, that you're producing simply by playing by these rules, the entries in those table correspond to actual equalities of values as you run your program. So that's great, but the collecting semantics is uncomputable because, well, you don't even know if it's going to terminate. So to solve this, we're going to lean on abstract interpretation, where with every collecting state, we're going to come up with a corresponding abstract state, and there's only going to be finitely many of those. So it's going to terminate. And the key property is that as you step the collecting semantic state, there's a corresponding way to step the abstract semantic state. Additionally, in addition to keeping around like which call you're at and what the environment is, you're also going to keep around the same kind of sharing table, and you're going to play by the same kind of rules and do the same intersection. So you use the same way to derive facts in the analysis as you do in the collecting semantics. And that makes soundness really easy to formalize. The facts that you determine in the analysis simply have to be a subset of the true facts that you found in the collecting semantics. And we've also formalized that in Rock. So we wanted to look at how precise and how scalable this analysis was. And to do that, we compared 4 different analyses. The first is that thing might be uncomputable, but for our benchmark programs, you can actually run it and it will terminate. So that's kind of the ground truth of the best possible information you can get. And that's looking for actual equalities of values. And then in the third column here, I have our environment sharing analysis, which is doing the abstract interpretation. And we found that in almost every case, we actually find the ground truth, which means that there's no knobs that you need to dial up on your analysis to find better information. On our benchmarks, we're doing the best that you can possibly do. Third, we compared against some previous work called lightweight closure conversion, which can be adapted to produce this environment sharing information. And we find that on a number of examples, we produce significantly more information than what that analysis does, up to 1.5 times x. Finally, since we improve over a previous analysis, we should also improve over what lambda lifting does to known functions. And we indeed see that that's the case on these same examples and on more. And finally, this is super scalable. Nucleic is like a 3,000 line program, and the analysis runs in about 20 milliseconds. So no issue there. So that concludes the analysis portion of the talk. Now I want to tell you how you can use these facts to actually transform your program. So as we saw in the introduction, there's multiple ways that you can transform your program. Maybe you provide n to f, but not to h, or maybe you provide it to both. So either way, what you have is a function which is going to assign to every call and every function in your term a set of variables that you are going to provide to that call or function. So for every call, you're going to add arguments according to this set. So if we associate the set n with the call k applied to 6, that means we're going to add n as our argument. And if we associate n with our function, we're going to add n as a parameter. And the first thing I want to note is that only some of these d functions are valid. In particular, you have to respect the semantics of the program, meaning that you should be a subset of what the analysis tells you. Second, suppose that you provide a variable at a call. That call might invoke 7 different functions, and you're adding an argument, which means you need to add a parameter to all of those functions. So you better take in x and transform all of those functions. Second, once you provide a variable to that function, those functions might each have an additional 3 locations where they're called, and so you also have to transform those call sites. And so what you get is this big entangled collection of functions and calls, which all have to be transformed uniformly. So stepping back to our example, here are the 2 groups of functions and calls that need to be transformed uniformly. We have f and its call, and we have h and its call. And we can assign a decision function on the right-hand side. So one choice is to provide n to f, but not to h. That was the first example. That doesn't do as well because now h has extra allocations. We could provide it to both, which is what we saw was good. But if you recall in the analysis, we also said that h shares f, which means that you could also provide f to h. And this, of course, is not something that you want to do, not only because you're already passing f to h, but because h doesn't actually use f as a free variable. So on top of these valid decisions, we have 2 additional properties for how to make good decisions. These are heuristics. So the first is that if you provide a variable to a function, it had better be used. And that means that it's either a free variable of the function that you're giving it to, or the function that you're giving it to then provides it to someone else. The second is that closures should not get larger as a result of this transformation. So you're not inducing extra free variables. So this means is that if you have a function with a call inside of it and you'd like to provide a free variable to that call, or you'd like to provide a variable to that call, it should either be a free variable of your function, so you know it's going to be available already, or that variable should be able to be provided to your function. So in order to produce these decisions or these conservative decisions, you can calculate it with a least fixed point procedure, and that's in the paper if you're interested. So then we can go to our results for this, our evaluation. So what we did is we took an instrumented interpreter and we ran it, and we wanted to check how many closures are you allocating and how many free variables are you allocating for all of those closures. And so you can see that some programs, like Knuth-Bendix have like a 2.5x free variable to closure ratio, whereas ratio regions has something closer to 15. In the fourth column are the percentage of bindings that we're saving. So what I want to highlight here is that lambda lifting is doing a lot of work for you. It's really good, and that's why we already do it. But if you take our analysis and also do that, there are a number of programs where you are doing significantly better than just the lambda lifting. So even large programs like nucleic and ratio regions and a ray tracer. And finally, there's opportunities for improvement based on these heuristics. So the conservative decision is nice because it has these properties, but you can save even more allocations if you're more permissive with your policy and pass as many things as possible. So it might depend on the particular program that you're looking at if you need to use some more advanced heuristic to pass extra information around. And finally, I wanted to go over an application that we have an eye on for this 3CPS compiler. And that's at runtime, when your machine is actually doing its thing, you have a stack, which is composed of stack frames, and variables are implemented on these stack frames. And that means that when you make a closure, what you're going to do is copy individual bindings out of the stack and go and stick it in the heap. We propose an alternate closure model, where instead of packaging individual bindings and sticking those in the heap, you actually just package a pointer to the stack frame that they live on. So this is like the difference between calling by value or calling by reference. You're copying a pointer to the thing instead of the thing itself. And to get an individual binding, you're going to load off that stack pointer plus an offset, which is statically known because you're the one doing the compilation. So the caller provided environment transformation in this setting means that instead of passing individual variables around, which there may be many of, you're passing around a relatively smaller number of just frame pointers and then loading off of those in order to access your environment. And apparently, this is not actually a new idea, and this is actually where our original motivation for this work came from, is way back before my time, there was this machine called the Algol 60 machine, which had dedicated hardware registers for these frame pointers. And you would have one frame pointer for each level of nested function that you have. And then Algol programs are mostly first order. So if I have some deeply nested function like f3, and it calls another function g2, well, f3 is going to have frame pointers for f1, f2, and f3. And g2 needs to be provided access to the frame pointer for f1. So that means since we're in the first order world, when we call g2 from inside of f3, we know statically that some of that environment is going to be shared, and we can just leave it in those dedicated registers. And so we would like to do this in the higher order setting in 3CPS in the future, and this work is like the first step to doing that. This is my conclusion slide. So what we've presented is an environment sharing analysis where you can propagate these sharing witnesses forward through this table, and you play by the same rules in the collecting semantics as you do in the abstraction, and that gives you a very nice way to decompose your proof. We found that this was fast and precise, and we submitted both our rock proofs and our compiler implementation, and both of those are available as artifacts. And then you can use this information to do caller-provided environment transformations. There's more applications than what I presented here in the paper, so you can take a look at that if you're interested. So here are our emails, and I'm on the job market for the next year, so please come and talk to me if you're interested in hiring someone that does program analysis, optimization, and compilers. Thank you.
Please, for any questions, walk to the mic and ask your questions.
Hi, I'm Simon Peyton-Jones. As I understand it, I'm interested in the payoff that you get from doing all this, right? So as I understand it, instead of heap allocating a closure for a lambda and then passing it to a function that then passes it to another function and so forth, instead you're going to pass the pair of the function pointer and its free variables down, essentially, because you've got to provide it to the high order function, and then it's got to pass it down. So you sort of pass down two things instead of one down your call chain, right?
Yes,
and that might be a good thing. It might do less heap allocation, but it might be a bad thing too.
Yeah, so there's
So
a
how do you
trade-off
know?
here. Yeah.
How do you know whether it's a good thing?
So I think it depends on whether memory pressure is worse for you, or whether providing these extra things is worse. That's why we're looking at the frame pointers, because you have to pass a lot fewer things. But you don't necessarily have to pass it down the whole way, because the place where you invoke that function finally might be a closure that actually has to package up the variable. And so you don't necessarily pass it down all the way. You just you create your closure initially with no environment. You pass it along with no extra information. Once you get to this other function, which is a closure that has packaged the variable, then you pass it there. So you're not necessarily always passing around this pair of a lot of information. Sometimes it's just available for you when you call it. So that's you can factor that into your heuristics when you're designing when to do this transformation. If passing extra arguments really induces a lot of pressure on whatever you're compiling, then you can try to turn that down. Yeah.
Martin Elsman, University of Copenhagen. Can you comment on a little bit on this precision that you're actually tracking all variables in scope and not only the ones that are free? What that buys you?
Yeah. So so if I go back here to the example, so our analysis sees that h can provide n, right? But if you're only looking at the free variables, at what's available already, you wouldn't notice that h would actually share n with the ambient environment, because it wouldn't package n, right? So when you're stepping through the analysis, h is technically allowed to reference n, right? It's lexically in scope. And so when you do the collecting semantics, you track all of the things that are in scope to give you the best possible information. You're absolutely allowed to filter that away if you want to after the fact and only track the free variables. That's still sound. It just gives you less information.
Hello, Matthias here. You had a good slide about how fast this is.
Yeah.
And you sort of mentioned our big program was like 3,000 lines, like spoken like a true academic.
Yeah.
So the question is, I have sort of two questions, like how does it relate to real-world programs in two senses? So first, do you have any idea how it scales for like much larger programs? And second, do you have to do this as a whole program analysis, or can you do it in modules, or separate compilation, stuff like that?
Yeah, so you can do it as a modular analysis. You just have to detect what's escaping and what's not escaping, and you're allowed to optimize the things that don't escape. Yeah. For this implementation in particular, it's still a research implementation, which means when I programmed it, it's still tunable with what the precision is of the 0 CFA or the K CFA or whatever. Now I have engineered it very well so that it's nice and fast, but if you did you could implement a very simple version of this that could run much faster. So right now it's done in two phases. The first is you compute this abstract state space of all the states that you could visit, and then you post-process that to figure out what's shared between the things. And so you could combine those phases. You could do something that's not so generic over your precision dials, and instead just track one thing per variable. That would work a lot faster. You'd get maybe a 3x improvement or something like that.
No, I'm not interested so much in constant factors. I just want to know if it blows up quadratically or exponentially, or if it's mostly n log n. Or
yeah, so your worst case is O of n cubed, or maybe more if you have lots of free variables in your program, but typically it's fairly small. So you could see blow up for certain programs, but we haven't seen anything like that, right? Your worst case, it always looks like some n cube plot for static analysis, and then you run it, and in practice, it's like not actually too bad. And that's our experiment, or our experience with all of these analyses as well.
Thanks.
Let's thank the speaker again. All right. Our next talk is multiple resumptions and local mutable state directly. Serkan, off you go.
All right. Welcome to my talk. I'm Sarka, and this is a joint work with Philip, Michel, and Jonathan. And I will talk about multiple resumptions and local mutable state in the context of effect handlers and the effect programming language. First of all, what are effect handlers? Operationally, you can think of effect handlers as a more general form of exception handlers, where the handler is able to resume computation from where the effect was performed. We have multiple options here. The handler either does not resume. In that case, it behaves just like an exception handler, or it can resume once. We also call that a single shot handler, and that is and that allows you to model stuff like coroutines and generators in your program. But you can also resume multiple times, and this allows to do really cool stuff like non-determinism and backtracking, logic programming, a lot of stuff. Right, but multiple resumptions are usually believed to be very inefficient to implement, and there are languages out there that explicitly disallow multiple resumptions to remain in the more efficient world. Also, multiple multi-shot handlers are make it more challenging to support local mutable state efficiently. And then in this talk, I will present the compilation of the effect language that supports multi-shot handlers and local mutable state, while keeping a constant time overhead for single shot handlers, which are the most common form of effect handlers. Okay, let's first look at a few examples. Effect handlers first needs effect operations, and this is how a signature of an effect operation can look like. In this example, emit takes an integer argument and returns unit, and is used to emit values like in a generator. And this operation can then be used in this example range, where we are emitting all the values in a range between two integers. And note that the function itself returns unit and only produces the values through this effect operation. And to actually call the range function, we need to provide a handler. And this can look like this. Here we have a sum function that takes an emitting program and wraps a handler around it by first allocating an accumulator, initializing it to 0. Note that this is a mutable variable. Then it installs a handler where it runs the program and returns the current state of the accumulator. And the handler takes care of adding the value to the accumulator and resuming with unit. And if we now call sum on the range of 1 to 5, we get the output 10 as expected. Here's an example that uses multi-shot effect handlers. We have an effect operation flip that returns a Boolean value which can be used for non-deterministic computation. And the handler for flip wraps the given program in a singleton list, and the handler then resumes twice, once with true and once with false, and also concatenates the resulting lists. Basically, this handler goes through all possible paths and collects all the possible outcomes. Now, what happens if we use multiple effects? In this example, we are first emitting 10 and then do a coin flip, and depending on the result, we emit either 1 or 2. We can compose our handlers from before by first first traversing all the possible paths, and then summing up all the emitted values. And that would output the value 13. But we can also handle the effects in the opposite order. In that case, we collect all the possible sums on each possible trace. And that would give us the list of 11 and 12. It's important to note here that the handler sum it also includes a mutable variable, and the state of that variable is resetted whenever the handler for gather resumes. Otherwise, we wouldn't get the desired output here. Now, what do we need to implement effect handlers? We need a few basic operations for that. We need to be able to enter a new context, and we need to be able to exit that context and take a snapshot of it, or to capture the continuation there. And we need to be able to restore this snapshot and continue the computation. For that, we're using a few operations known from multi-prompt delimited control. First of all, we're having the reset operation, which on this abstract call stack here just pushes a delimiter or prompt onto the stack with a freshly generated label. Also, in the environment, we're storing this fresh label in the variable p. Then we can, after we've built up stuff on the call stack, we can shift to the label that we've captured earlier. And that would include looking for this label in the call stack, and then taking it all off from the stack and storing it in the variable k. Finally, we have the resume operation, which takes such a captured continuation and pushes it back onto the stack. It's important to note here that k remains in the environment and might be used again. That's how multi-shot effect handlers work. It's also important to note here that there might be mutable variables within this k, which keep their state at the captured point. Now, to implement these three operations, we have a few challenges we want to address. First, we want to avoid traversing through the stack and looking for a label. This problem has already been solved for single-shot handlers by this paper, Lexical Effect Handlers Directly, where it was shown that we can use direct pointers to the delimiters for lexical effect handlers. And we are generalizing their approach to also work with multi-shot handlers. Second, we want to avoid copying continuations in the case of single-shot handlers. And for that, we are relying on our memory management technique, which is garbage-free reference counting. This provides us during runtime with a count of how many references we are having to a continuation. And then we only copy if we have more than one reference. Finally, we also want to avoid traversing a continuation when we are resuming them in the case of single-shot handlers. And for that, we introduce a notion of valid and invalid continuations that differentiate those that can be resumed in constant time from those that need to be adjusted first. Now, how does all of this look? It all boils down to how we represent the call stack that we've seen earlier in memory. Instead of one stack, we are using a linked list of stacks, which we also call the meta stack. And instead of maintaining a stack pointer, we're maintaining a meta stack pointer, which is this MSP here. Also, each stack is paired with a separately allocated prompt, which represents these delimiters on the left side. The delimiters themselves are not included in the call stacks themselves. Right, and finally, if we have a label on the left side, this p equals number 1, we instead store a pointer to this prompt 1 here. That also means that the label itself is actually not included in the low-level representation. Now, in this setting, if we want to enter a new context, or if we execute reset, we just allocate a new stack and a new prompt, and link it to the meta stack. Also updating the meta stack pointer. Then, if you want to execute shift, we're passing a pointer to the desired prompt. So the prompt itself might be arbitrarily deep in the meta stack, but that doesn't matter since we are having a direct pointer to it. From there, we go to this next state where we update the meta stack pointer to the next stack in the chain, which is after p. Also, we take the stack of p and link it back to the first stack from before. And that way, we can just return the pointer to this last stack and also have a constant time access to the first stack. And if you only had single shard handlers, then we could just reverse this operation to resume a captured continuation. But since we also have multi-shot handlers, there are a few things to consider first. First, we need to see whether we need to copy the continuation. For that, we look at the reference counter of the stack, and if it is 0, meaning that there are no other references to this, then we know that we don't have to copy it. Otherwise, if it is not 0, then we must copy. And how does copying look like? If we copy a stack, the copy still points to the same prompt as before. But this introduces a problem because the prompt can only point to one stack at a time. And we are calling the stack that is pointed to by the prompt valid stack, and the other one invalid. And we also introduce an invariant at this point, that the meta stack may only contain valid stacks. Now, with that, we can copy a whole continuation by copying each stack individually. But now, of course, we cannot resume the copy because these stacks are all invalid. Now, if we want to resume in a possibly invalid continuation, we first have to revalidate all the stacks. And for that, the straightforward approach would be to just iterate through all of the stacks and to redirect the prompts individually. But of course, we're having the goal of constant time resumption for single shot handlers. So we need a way to check in constant time whether we need to revalidate anything. Because as we've seen earlier, the shift operation keeps the prompts all in a valid state. And they might still are. For that, we introduce another invariant here. Stacks in a continuation are either all valid or all invalid. And that way, we can check the validity of a continuation by just looking at one stack. And of course, when we have an invariant, we have to maintain it somehow. In this case, whenever we revalidate a stack, that might invalidate other stacks because we are redirecting the pointers around. And in that case, we have to invalidate the whole continuation that the stack was part of. Right, to summarize, resuming is done in 3 steps. First, we look at the reference count and copy if needed. And then we check the validity of a continuation and then revalidate if needed. And finally, we link the continuation back to the meta stack. And all of these steps are always, the 2 checks we're having here are always succeeding for single shot handlers, because for single shot handlers, we are never copying anything. And if we never copy, we also never get invalid stacks. Right. Also, one more thing to mention here, the implementation of mutable state is very straightforward in this setting. We can just allocate the variable onto the stack, and as a reference, we can not store the direct pointer to it, but we are storing a pair of a prompt pointer and the offset within the stack. And that allows us to reference this variable later by just adding the offset to the stack address. Great. Now we have implemented this compiler in the LLVM backend of Effect, and for that we also ran a bunch of benchmarks. We're using a set of benchmarks that are explicitly designed to measure effect handlers in many different languages. We're comparing here to Lexa, OCaml, Coca, and F, and also the old Milton backend of Effect, which is now deprecated. On this plot, you can see the relative performance of the other languages normalized to the performance of Effect. Bars that go up are faster than Effect, and bars that go down are slower. You can see that in most cases we are pretty fast. A lot of downgoing bars here. And there's also the differentiation here between lexical and dynamic effect handlers. The lexicals are represented here in orange and the dynamic ones in blue. And we have one special benchmark here, checkpointing, which we added separately to the set of benchmarks. This benchmark is specifically designed to rely on both multiple resumptions and local mutable state. And this is not supported by both Lexa and OCaml. So that's why we're having a bunch of X's here. And we could only run this example on Coca, which performs a lot worse than Effect. Also, we are using the geomean here, so the geometric mean of all the other benchmarks. And as you can see, we're performing relatively well, while having a language that is more expressive than others. Right, there's still one limitation in our implementation. The prompts that we've seen can always only point to one stack at a time. And that means that the meta stack can never contain multiple stacks that share a prompt. And on the source language, that means that we can resume multiple times, but we cannot resume a second time while the first resumption is still running. And this means that we can do the 2 resumptions on the left side, but on the right side we are seeing what's called bidirectional handlers. That means just that we're resuming and immediately resuming again, and that is not allowed in our runtime. Right. To conclude, we have a language with multi-shot handlers and local mutable state, and we have constant time continuation capture and resumption for single-shot handlers, and we have a constant time access to mutable variables. In the paper, you can also find a formalized intermediate representation with the semantics on a stack-based abstract machine, and a full translation to an idealized assembly language. And with that, thank you for your attention, and I'd be happy to answer any questions.
Kimi Yo. The second last slide about not being able to resume inside the resumption. Can you say something about types? Do you have a type system that doesn't allow that? I mean, what happens when you do actually have such code? It just blows up in runtime.
We don't have a static guarantee that exclude these cases, but we do have we can detect this during runtime, and in that case, we just abort the computation and panic.
So you detect it during runtime?
Yeah.
Hello, I have two questions, actually more to test my understanding. One, when you say mutable state, if you resume thing multiple times, do you reset all the mutable state? Does it look like all the mutable state is reset?
Can you repeat that? Sorry.
So suppose you have a counter that counts how often you have emitted. And if you resume it multiple times, does the counter get reset to whenever you created it? Okay, that's how, but can you do the other multiple state that basically has a global counter, for example? Could you do that in your system? I don't know if it's useful or just...
I'm sorry,
suppose I wanted a global counter that doesn't get reset as a mutable state.
Counters reset whenever we resume.
When you resume, yeah.
Yeah, if we resume 10 times, the counters reset 10 times.
Yeah. My question was, can you make one that doesn't get reset in your system?
Only if the state is captured by the handler. If this state is allocated outside the handler, then
that makes sense.
it is not resetted.
Okay, and one tiny other question is, you're doing the elision of copying if there's the reference count is like basically there's only one reference. I think, or just my question is basically, does it save more than a constant factor in runtime? I assume it does, but I don't know. Like if you instead did always copied, you didn't do the reference counting check, you always did the copy, would it slow down your program by more than a constant factor? Like you have this clever thing where you check how many references do I have and then I don't copy.
Yeah, in this case.
How bad, if you didn't have the check, how bad would it be?
I'm sorry, can you repeat the question?
Okay, so you have this reference counting. You don't do a copy if you only have one reference in your program to it. And my understanding is that this one saves a lot of time and it basically saves arbitrary amounts of time, but my suspicion is that it may only save you constant factor. Like it only makes the program twice faster or 3 times, no matter what. But I don't know if that's true. I assume it probably makes your program, instead of quadratic runtime, you can have linear runtime or something.
Yeah, I mean, if we have to copy, this would not be constant time at all, right? It would scale with the size of the continuation.
And that can get arbitrarily large at runtime?
Yes.
Okay, if you have a deeply nested thing. Okay, yeah, thanks.
Any other questions? I had a question. So your restriction means that I cannot run these things in parallel, right? I would like to run these continuations, like copy them multiple resumptions on multiple cores in parallel. So your restriction where you had in the last slide, that would mean that I cannot use the system for parallel programming, right? I have a continuation. I want the same continuation to explore false on one core and true on the other core, where you had this flip example.
Well, in the flip example, the first resumption is done computing when the second resumption is executed, right? So that is not that's not a problem with our limitation. And in fact, we have never really encountered the limitation in practice, even though we have a lot of examples with thousands of lines of code.
But is the effect a parallel language? Does it execute things in parallel at all? effect language.
Parallel
Yeah.
execution? No, we don't have that.
Oh. All right. Any other questions? No? All right, let's thank the speaker again.
It says mute. Huh?
That's all.
That's mute. Okay.
All right. The next talk is OCaml Blockly by Kenichi Asai. Please go ahead.
Thank you. Okay, OCaml Blockly. Block-based programming is becoming very popular. You can see Scratch, Google Blockly, Alice, Snap, and they are very nice in various aspects. But here I want to concentrate on the technical part, and they avoid syntax errors, so that's very nice. The slogan is, once a program is constructed, it runs. Okay, are we satisfied with this? Any decent language requires us to make syntax error, requires us to avoid syntax errors, but we also have to avoid unbound values. So it's lexical errors and also type errors. And for type functional languages, correct syntax is not enough. So what I want to do is to build an OCaml variant of Blockly, and where we encounter no syntax errors, no unbound value errors, and no type errors. So once a program is constructed, it really runs. And so let's see how it looks like. So this is the OCaml Blockly, and I define one function, variable 1 there, and let's say it's 1. Whoops. Okay, and this variable 1 can be used within only in its scope. So if I drag it there, okay, the tips is in Japanese, but it says it's out of scope, so you cannot drop it there. But you can use it within its scope. So I can use it to define 3 there. But below there, we see that f receives its function argument called 1. So it means that if you use this 1 there, then we cannot use it because it is shadowed. So if we rename it to some, okay, if I rename it to something else, then I can use it there. And if I hover on the variable, then we can see that all the same variables are highlighted. So it knows where it goes. Okay, so let's now construct the factorial function. So in the else branch, I would say, okay, times, and n. And then I want to make a recursive call there. Okay, I can do like that, but sometimes we don't want to construct a program top-down, so that we don't want to construct the outermost construct first, but we want to construct the innermost one first. And that is not allowed in this language, because if we want to make n minus one, it is not allowed there because n is out of scope there. So to accommodate the bottom-up construction of programs, we provide a scope playground. So each let expression comes with scope playground, and in the scope playground, we can see that all the free variables that are available in that scope is there, and we can use those variables there. So here I can see 1, 3f, and factorial because it is defined as a rec. And then we can also use the variable n and make n minus 1 there. And make a recursive call there. And, oops. And we can plug that in, oops, why not? I think I should, yeah, like that. Okay, let's say we want to compute a factorial of 5, but I cannot do that there, so I introduce another expression there and say factorial. And if you say factorial of foo, of course it's a type error, so you cannot make it. So, say factorial of 5 and run it. Oops, oops, okay, okay. Well, I'm very sorry, but it's not connected to the internet, and it says it cannot run. But okay, you can run it, but you will see the standard text output of the standard OCaml. Okay, so that's the OCaml Berkeley. Okay, so no syntax errors, no unbound values, no type errors, and bottom-up program construction is done in scope playground. So in a nutshell, OCaml Berkeley behave as we language designers expect. So how is it perceived by students? I use the OCaml Berkeley in my functional language course, 90 minutes flipped class once a week and 15 weeks. And I introduced OCaml Berkeley in 2019. And students either use OCaml Berkeley or Emacs equipped with Turing mode and Marlin mode. But at week 10, they all have to move to Emacs because OCaml Berkeley does not support variants, so we cannot program with trees. At the end of the course, I ask students some questionnaires. So these questions are somewhat naive, and what I really want to do is that we want to see if the use of OCaml Berkeley has any effect on the educational part of the, educational part. But because OCaml Berkeley was not built as an educational research project, but because I built it because it will serve students very much. So those questions are not considered as a research project, but I just asked them. But still, I want to extract some information how students perceived about the OCaml Berkeley. So when did students stop using OCaml Berkeley? So some students did not use it at all, and some students abandoned it after several weeks when the program gets bigger. But rather surprisingly, quite a number of students use OCaml Berkeley all the way to construct the shortest path problem for the Tokyo Wet Metro network. And before the OCaml Berkeley support is ended. And in the free text comments, as well as I made an interview to the students in 2023, and they say something like that. So throughout, some students did not use OCaml Berkeley because, they thought they need some training in writing texture programs. And at some point they understood syntax, then they move on to the text-based programming. But many people use OCaml Berkeley quite a long time. And I asked them, well, how can you make such a big program like shortest path program using blocks? Then some of them replied that the length of the program does not matter. Well, if the program becomes bigger, then with texture programs, it still become hard to comprehend what's happening there. Then if you are using OCaml Berkeley, the structure will be simpler to understand. So students appears to acquire their own way of understanding programs. So they grow with blocks, they have some intuition about the blocks. Okay, did students find OCaml blockly useful? Okay, something like that. Well, some students say it's good for only for small programs, but most of the students say it was nice, and there were some deeper comments like I could concentrate on programming without being bothered by syntax, or once become used to OCaml blockly, writing text programs became easier. So that's quite nice. And rather surprisingly, many people said they are more aware of types. And it was used for detecting type errors. And yeah, that kind of answer was quite popular. And so I wonder how they understand the type concepts through OCaml blockly. And in OCaml blockly, a type has its own connector shape. So that's the integer, and that one is Boolean. And so I asked students, did you remember the connector shapes? And some said yes, some said no. And I tested them, and okay, so that's the result. And typically they remember simple types, but they do not parse the complex ones. So that is a block for forward right. And that big thing is the higher order function. And that connector shapes that, yeah, shows that. And they don't parse that, but still they can see that, oh, that part is complex, so that part must be a function. And so it seems they use that information there. It seems that how they acquire the type information, anyway they try to connect all the things. And when they are rejected, okay, I have to think somehow there. And interestingly, anonymous, well, vast majority of interviewees said they recognize colors. So they feel, some of them say they feel something from the color. Okay, that's warm, or I don't know. But so it's so currently colors of OCaml blockly are based on types mostly, but not quite. So this one is a float of int, so it has the color of float, but it accepts the argument in integer. So that integer part is not in blue. So if we redesign so that the colors reflect type information more, maybe that has some good impact on students. Okay, do you think program got easier using OCaml blockly rather than using textbooks and text-based programming? Like that? Okay, some say I did not use OCaml blockly. Okay, that's okay. And understood only when writing programs in the text editor. So some students said, well, they need to write text programs by themselves rather than tinkering with blocks. And some neutral students said it was useful, but not sure if it leads to deeper understanding. So I asked something like, do you think the use of the OCaml blockly was beneficial to understanding the deep concept of programming? Okay, I understood the concept, but I don't know if it's because of the OCaml blockly or I just learned it. So, okay, this is a reasonable comment. And some said, well, some said it is too useful. So you don't have to think, but you can just plug it in. But I would think that that's not a big problem because, well, you will have to think anyway to construct a decent program. So I think that's okay. And vast majority says, well, syntax support was useful, typing support was more useful, and in particular, beginning students were empowered. So some students thought they will not be able to write shortest path program anyway. But then they were introduced to blockly, and okay, they were very encouraged by that. And I also asked, did OCaml blockly have negative effects in that when you transfer to text programming, do you think it was, well, you couldn't write text programs at all? And okay, so the result is something like that. Most people said it was okay. And some of them said deeper than that. And I learned how to write programs in a text editor. So they are doing OCaml Blockly, but still they thought they learned programming in the text editor. Also, I became able to program in other languages too. So it is nice. I think they learned something there about the syntax. And neutral part, well, they say, okay, it was too useful, relying on it too much. And also some negative comments said I could not write any programs in text editor when switched. So when they switched, they were completely white with whatever they get. Okay, so they had no clue what to do there. So because I didn't have any question on the transition to text programming, I interviewed the students, and almost all students said the OCaml block was nice at the beginning, and they could get over the syntax problem at the very beginning of their program quite easily. But when they switched, they were confused. Yes. Quite a number of people said that. But I think that is not a big problem because they became able to write programs at the end anyway. And so they have to struggle somewhat. But at that time, they already know the basic structure of OCaml programs. And then they can write if statement, for example. If you say if, then you have to say then and else. And also, some of them said that their ability to write texture programs would not be lower if they started programming text-based programming from the beginning. So I think that's a good news. Okay, you might say that Visual Studio Code with the OCaml platform would be enough. Well, they provide all those information to you. And my answer is that OCaml Blockly supports the very beginning students, and they do not know how to write if statement. And if you cannot write that part, then you cannot get rid of those wavy lines that VS Code provides. So I think this is OCaml Blockly has some role in the education for the very beginning students. So summary and status. So OCaml Blockly avoids syntax, scope, and type errors, and bottom-up programming is via scope playground. And beginners do suffer from those errors, even for the CS major students. And and in particular, OCaml Blockly supports beginning students. And transition to text-based programming, I think, does not appear to be very hard. And current status is that it's rather miserable. After the main developer graduated, I maintain it by myself. It's a big system written in JavaScript, and it's almost impossible for me to maintain it, not to mention improve it. And this year, one of my undergraduate students was interested in that, so I tried to extract the essence of OCaml Blockly. That is different from the Google Blockly to OCaml Blockly with that undergraduate student. But she's graduating in several months, and she's not coming to graduate course. So I think OCaml Blockly has some merit, and it's an interesting system to learn functional language. But it's maintenance in danger, and if you are interested in it, I'm happy to collaborate. Thank you very much.
Please walk up to the mic for questions.
Thank you for the wonderful talk. So I understand block languages are mostly used for learning programming, but I'm also wondering whether it would be useful for people who already know the language to actually step back and be forced to think about programming in a more structured way. Have you had any students who started using Emacs and then later on went back to using OCaml Blockly?
Basically, no. And I don't think, well, at least this OCaml, well, say if you have projection or editor, and that's for experts. But for the OCaml Blockly, well, one of the reasons is that it's not polished enough. So the expert will complain more You can see, well, you can see the structure of the program, yes, but I doubt it will be useful for.
Well, I think students might still be able to better understand the binding structure,
Yes,
for example. And student complaints are fine, right? It's fine if students complain. I don't mind students complaining if they still learn.
So block-based programming is great for not getting syntax errors, but it doesn't scale very well to larger programs. So people who work in educational computing have been thinking about this for quite a while and develop so-called frame-based programming languages like Stride or Greenfoot or BlueJ or Elan. Have you thought about just maybe appropriating, just as you've tried to take the lessons from block-based languages, what about taking the lessons from frame-based languages, which might actually be a better fit with OCaml than Scratch-like lessons? Yeah.
Is that I want to help my students, and for my case, this is what is needed. So they had 1 year of C programming, but they are very new to OCaml, and they are not very strong students.
Sure. So, but these frame-based programming languages are directed at exactly that class of students. So my question is, did you consider using that?
So far, no.
Okay,
And
so worth a look.
Okay.
It's a very good
Okay,
stream
yeah.
of work, mainly at King's College in London, I think.
Hi, thanks for the talk. What are the limitations? How far does this get into OCaml? In terms of like how many, what features of the language does this cover? Can this work with libraries? Sort of how, like.
Not much.
Okay.
Well, it includes the list library, and it includes record definition, record type definition, a match statement, but not variants, not exceptions, not modules. Not modules.
Okay. Thanks.
So you used the shapes of connectors to indicate types. You didn't say anything about polymorphism, though. I wondered, what if you have a polymorphic identity function, for example? Is it a block that changes shape depending where you put it, or what happens?
Yes, it changes. It has special connector, and if you connect it, then that one is instantiated. So it supports late polymorphism, so Hindley-Milner late polymorphism.
Right. Okay, so welcome to the afternoon session of ICFP on semantics with 4 talks, the first 2 being JFP-based talks. And the first one will be given by Paul on a contextual formalization of structural co-induction.
All right. Thank you very much. My name is Paul Downen, and I'm here to tell you a little bit something about co-induction. So in contrast from something we all know, is induction is an insanely useful tool. We use it all the time, all over in programming languages and just programming itself. And it's the kind of main workhorse. But sometimes you need something more, right? So lots of programs will interact with the outside world, take inputs and outputs while they run, right? This is kind of co-inductive in nature, and there's lots and lots of examples of this. You can kind of think of a web server or operating system are classic examples. And it also comes up sometimes when we study the semantics of languages, right? So we reason sometimes about bisimulation and dealing with infinite processes, or when you want to reason about some kinds of effect systems, there's different techniques that use that. So I mean, idealistically, I should just be able to use co-induction the way I sit down and write a paper for JFP or ICFP or one of these conferences, and I do a proof by induction. So let's just do a co-induction. I mean, what's so hard about doing co-induction anyway? It should not be a big deal. So here's a super basic hello world for co-induction, right? So I've got infinite streams where there's always more elements in the stream, and each stream has a head and tail, right? So head is the first element, the tail is the rest. And here's just a super simple mapping function that, given a function, we're going to apply it to all of the elements in a stream. And we want to know that if I map the identity function, which does nothing, on a stream, I get back the same stream. So how do we prove this? Well, you know, one way might be general co-induction, right? So we say by co-induction on the stream. And so we assume the co-inductive hypothesis that mapping the identity over x's is x's. And well, this is a really simple proof, right? I mean, there it is. That's what I had to prove. So I'm done. QED, easy, right? So you all believe me, of course. But maybe something feels wrong about this. I mean, I should probably say something about map, or I'm not really doing anything. So this feels wrong, and it is wrong. So I should probably do something, right? So I should maybe inline the definition of map and then do a bit of calculation and show that I wound up where I started again. Okay, now this feels a bit more like a proof, and what's different this time? I mean, technically everything I did before was correct, quote unquote, but obviously it's not a real proof. And what's different this time, and it's kind of the typical sort of technique is, okay, I use the co-inductive hypothesis only in a productive context or a guarded context, right? So I've only used it in the context in which I've applied a constructor. Right, and this is a typical kind of restriction that we will use of, okay, the co-inductive hypothesis is a little bit much. You can only use it sometimes. All right, so if that's the case, then hey, maybe here's another theorem. So the other one was a bit of an easy warm-up because it's obviously true. Here's another one, which would be very adventurous, that the stream which starts with 0 and then is always 1s is equal to the stream which is always 0. And it'd be very interesting if this theorem was true, because then 1 is equal to 0, and we're getting a very interesting mathematics if that's the case. So clearly something would have to happen here. And well, here we go. Here's a little bit of rewriting. You don't have to look too closely at all of it, but the idea is every line technically is correct, but obviously something must be wrong. And it's not really guarded in the sense, I mean, I've only used the co-inductive hypothesis in the argument of a constructor, so it's kind of guarded. But something else obviously must be going wrong, and it's because, okay, even though it's kind of like in a guarded context, it's not guarded anymore, because I've used tail. That's just actually the thing that's gone wrong. So it kind of looked like it may have been productive, but in actuality it wasn't, because of this like extra semantic content that is needed to actually tell if it's really guarded. So it's not purely as naively syntactic, or it's a little bit more nuanced than you might have thought. And this is like the problem with this whole enterprise, right, is that fundamentally the co-inductive hypothesis done this way is way too powerful, and it makes it too easy to create vicious cycles, so we have to restrict it to good contexts. And the problem is the division between good and bad context has this tricky semantic content about what somehow the meaning of these things are. And I kind of started in a very particular style of proof, which is a certain shape where we're doing a set of calculations. And you can kind of do it if this is your shape, but good luck if your proof is actually a few paragraphs of English prose, of analyzing English and understanding what is a good context there is, I don't actually know how to help you. But even in the setting, right, where we've got a particular shape of proof, proof assistants can help us, right? They can do some of these checks and they get it correct. That helps. But the experience is maybe not exactly what you want, and so let's look at kind of what that looks like. So here's a formalization of just these ideas, right, in a system like Rock. So we can define a co-inductive type for streams. I can define the mapping function, and well, we can't exactly prove that they're equal in the most simplistic definitional sense, but we can prove they're kind of like equivalent in the heads and the tails, right? So this is how we get going. And here's two proofs, and they're honest proofs in the sense that I'm not trying to cheat and do something silly like I did on the very first example, right? I'm actually analyzing it and going through. But there's a subtle change, which I'll leave you to puzzle out what the actual difference is. And if you write this into Rock and you start stepping through, it nods along and says, yes, there's no problem, everything's great. And you say, oh, okay, so there's no goals left. I prove my theorem, and then I hit QED. And on the right, it says, no problem, you're good. And on the left, it says, actually, no, you were wrong all along. And the only hint you have is you can try to print out the proof term that was generated. And in small examples, this is really hard. And in larger examples, it's essentially impossible. Try to figure out what happened. And I don't know. That's not what I wanted, right? This is not what I was trying to do. In the beginning, I was even just trying to sit down and on paper write a proof and know what made sense. And the issue is that when I do proofs by induction, there's kind of built in the guardrails, right? I assume in the inductive set that it's true on some n, and then I prove it on the next number. And I don't have the safety rule for co-induction. So what I actually want is a formalization or a formulation of co-induction where I have knowledge when I apply the co-inductive hypothesis that it will actually work and not have a problem without some sort of secondary syntactic check that I don't always have on pencil and paper. So let's look at another way, another kind of style of doing co-induction where we can do it with confidence without this second elaborate check. And the kind of idea where this comes from is the idea of copatterns, right? So this has been around for quite a while in a system like Agda. And if you're not familiar with it, that's okay. If you are, the point is that more of the structure is there and there's less hidden from you, and it gives you kind of naturally the right way to think about these things. And so let's look at what we all know, what's all familiar, and what doesn't have any problems is induction on the natural numbers. So the shape of this is to prove that a property holds on all of the numbers. We have to prove that it holds on 0. And then the inductive step is if it holds on n, it holds on n plus 1. So how do I do something with exactly this shape, but for co-induction? The trick is I don't
Sorry, the mic is on.
Ah. Maybe, is it, oh, this is way better. Okay, let me hold it back there. Is that a good volume? Okay, perfect. Yes. So we kind of calculate through, and the thing to notice here is all of that kind of fudging around about guarded contexts we can throw it out the window because the guard is the marker H from the co-inductive hypothesis, and the rewrite happens, right? So the kind of normal proof still goes through, but we don't need a secondary check. And that means we immediately get feedback when we try to do this for the broken proof that should never work, right? So somehow this kind of bait and switch that if I start with a 0 and then become all 1s, that's not the same thing as always a 0 forever. And let's see what goes wrong. So the head case does work because they both start with 0, so that's not where the problem is. The problem will be when we try to work out the tail. And before, when I tried to trick you, I kind of snuck in a little bit of distraction by expanding and then trying to apply the co-inductive hypothesis too far in. But now it actually just does not match. This does not match the co-inductive hypothesis at all. Not because of some weird productivity thing or secondary check. Literally, this does not match the left-hand side because the H is too far from the thing I really wanted to rewrite. It's just not a match. And if I tried to go the other way and trick in some other way, well, I could get started. I can apply the co-inductive hypothesis, but then I can never reach the other goal on the other side. So there's no way to make any progress towards bridging the gap. And it's not due to productivity. It's not due to some syntactic check. It's just the structure of the co-inductive hypothesis. So this is kind of the main informal idea. But how do we make this formal? How do we make it a particular actual system and come up with axioms that capture those ideas? And the trick is to use, rather than intuitionistic logic, a form of classical logic. And the reason is we need to give equal status to not just answers, but also questions. So we have both questions and answers we can ask at any particular type. And so a producer of a type A gives an answer that somehow corresponds to that type, and a question of that type asks a question, or a consumer of a type asks a question. And so the fundamental unit of computing is when you stick these two things together, right? This is the long ago familiar rule of merging answers with questions. And so if we start with the easy thing we already know, right? There's a few ways we could express regular primitive induction on numbers, the thing we are very familiar with. So a property is true if it works on any value. So what are all the values? Well, it could be 0 or y plus 1. And so the rule of induction is saying, well, if I've got maybe some unknown x in my context, I can work out some result by just handling these two cases. And in the inductive step, we have to work it out for any generic number, and all we know is that the property already works on it. Then we work on it in the n plus 1 case. Of course, we can summarize this as a closed axiom, which is sound and doesn't break our logic, right? We can just use this whenever. So the same thing, we can do that for streams as long as we talk about observations, right? And so observations here, they take streams as input. And now they only have two cases. Like the only two observations I can make on a stream is I ask for the head first, then I pass that to some observation wanting the A, or I can ask for the tail, and I pass it to some other observation on streams as well. And so here now, instead of saying I've got some unknown x, I've got an unknown observation that somehow processes streams. And we have the two cases, the head case and the tail case. And in the tail case, we have to say this works for any arbitrary stream observation, where all I know is that the property is established for it already. In this, unlike the usual co-inductive general kind of fixed point form, gives us an axiom for co-induction, which is closed and is sound and doesn't break our logic. So this restricts, or this lifts the kind of restriction we normally have to impose, that we have to check these things and make sure that they're used very carefully. We've actually got a sound reasoning principle that works. And just as a sort of quick example, I mean, streams are the typical simple example to get going, but they're kind of boring, right? This generalizes to all sorts of other principles as well, just by following the structure, right? So you could have, instead of infinite streams, infinite binary trees, right? They're kind of rivers that fork, and then I can go down either the left or the right path, and we can get sound principles for other structures like that too, just by following the shape. Okay, So that's kind of the general informal idea, something you can just do on pencil and paper without thinking too hard, and the main trick of formalizing these rules for reasoning about equality. But I don't know about you. Sometimes I like to compute things, and I want to know that my proofs about computation actually work. And so the minimum requirement is that if I say things are equal, then they should actually be equal in some sense about computation, which is typically contextual equivalence, right? So if I claim, the rules of my system claim that two programs should be equal, then if I actually run them in some arbitrary context, I should always get the same result. And this is kind of one of the main results in the paper. And the proof of how this is done is based on a particular type of logical relation using orthogonality. And because we've got these recursive types, we need to figure out the fixed points of co-induction and induction in some sort of subtyping lattice. And the main kind of key trick to make this work is that there's two ways to define recursion, two different ways to solve the fixed point, and they happen to coincide, which usually is trivial and is not quite so easy in this case. And this is interesting because, of course, as a corollary, the main one is that true should not be equal to false, which we extract from contextual equivalence, or that if I say that I've got two programs that all they can do is emit a Boolean answer on alpha, then if they're equal, either they both send a true to alpha or they both send a false to alpha and not something else. What about if my program has effects? And in classical logic, we kind of already have one baked in. So we need to be able to handle the case if there's something more interesting, like an effect happening. And I'll kind of mention that in this sort of setting, there's actually a maybe surprising wrinkle we normally don't think about, but there's information effects. If we erase or duplicate information, this has exactly the same sort of problem in the opposite way for certain other cases. So we have to think about that too. In certain cases with certain effects and certain orders of doing things, you can have inconsistency, so you have to be careful. But in reality, it's the exact same thing we've already known since forever, since dealing with any language with evaluation order and effects. So there's actually nothing new here, but we do have to do it correctly. So in particular, what that means for induction is if I'm in a call by value language, I don't have to worry, it's just all fine, it works. But if I'm in a call by name language, or something where there's delayed evaluation, we kind of have to be careful. If a program maybe loops forever or raises an exception, then there's a difference if I try to look at it and reduce it or not. And so if I try to apply induction in this call by name language where I care about the different things that might be raised or that it loops, I only can apply it in the case for equality. There's other propositions we might want to do, like for all and implies. But in the base case of two things being equal, I can apply induction if I'm actually using the x in a strict context. Then I can do induction on x, and I won't run into any problems, even if I'm in a weird call-by-name language with built-in effects. And well, you might not be as interested in that, but the other thing that does come up a lot is I might be doing co-induction, and if I'm in a call-by-name language, there's no problem, even if there's weird effects, which is a little bit odd. But if I'm in a call-by-value language, then we have to make sure that we don't apply the co-inductive principle kind of whenever. We just need to make sure that, and this is the only sense of productivity that there is, that the programs return an actual value of some form, two values, to the output alpha. And essentially, if you're kind of wondering what this means, this is exactly the same thing as the normal restriction in the lambda calculus. If I'm in a call by value lambda calculus, I can only eta expand or reduce values, not general terms. So you're kind of familiar about that sort of thing. It's the exact same property that we do there, and this is the restriction that stops you from doing that. Right? So it's exactly the same nature there. And you also might be asking about, well, what about other reasoning principles? Maybe I really, really like bisimulation. What if I wanted to do that? So all of these kinds of other ways of structuring a co-inductive proof are derivable. In particular, bisimulation is very popular. And you can derive that in terms of these axioms and these principles just as well. And the only caveat, it turns out, is that to do something like bisimulation or strong co-induction, it's the equivalent of strong induction, which means you assume the co-inductive hypothesis for all possible smaller observations, not just the next one. You need the unrestricted call-by-name rule, but you don't need that for something like mutual co-induction. That works kind of whenever. So that is my talk. I want to open it up for any questions you might have. Yeah. Maybe not. Yeah.
Okay, so if you end up writing an implementation, you know Jasper Cox in Agda developer. So he's just got people. He just got people that finished an internship with him that basically studied co-induction in Agda and compared the different methods. So there's a report that compares them. So if you have an implementation, that's a great way to see if it works or not in practice compared to what Agda supports. And Agda works mediumly.
Thank you. I think it probably will work.
Yeah, and
But
if you're not aware of it, there's a library for co-induction in Rock developed by Damien Plus and Yannick Zakowski. And it looks very similar in the ideas. They've never published a paper about it, but is your thing, I don't know what it is, like the math behind their plugin, because they've just written codes using lattices and stuff like that for co-induction. So are you actually providing a foundation for this kind of plugins they're doing?
Yeah, it might be from that sense. So I'm not familiar with that particular library, but a big part of the paper is kind of proving that this actually works, right? So this kind of theorem. So that might be what you're thinking, like the foundations that this is sound and kind of, well, I guess enough is implementing it and testing it in practice will be the interesting case there, yeah.
Well, actually, I'd like to see a slide.
Oh,
okay. Sorry.
Let me plug it.
Could you show the slide where you say like all observations on streams are either observations on the head or the tail?
Yes.
Because I was very confused by that.
There, that one maybe?
Yeah.
Yeah.
What if my observation is adding the first two elements of the stream? That involves both the head and the tail.
Yeah, of course. And this is kind of like the same thing of, saying that all numbers are successor or zero, but of course I might add two numbers, which isn't successor or zero, but it simplifies down to those. So for copying a stream and using both the head and the tail, it's saying we're copying it and we're running it 2 times with 2 different observations, right? And so that kind of has to do with those information effects that I said, duplicating some information and using it more than once.
Okay.
Yeah.
All right.
Yeah.
All right, so thanks again.
Yep.
Set? Okay. So the second talk will be given by Jacques on monadic equational reasoning independent type theory.
Is the mic working? I'm going to speak a bit slowly for a second. I hope the voice will keep. Okay, so if the last talk could be seen as well the theory behind the implementation, this one is more like the implementation of the theory. this is a joint work with me. What is monadic equational reasoning? It extends equational reasoning to monadic computations. And it was originally proposed by Gibbons and Haynes in the same conference. And how it works, basically it combines pure equational reasoning, which you probably have an idea what it is, with monadic laws. And the basic idea of equational reasoning is that the programs are the specification. So if you want to prove that the program follows the specification, it will be equal to the specification. Okay, and it had been implemented in Rock, it was Rock at the time, by the Monet library, which essentially provides a hierarchy monadic interfaces. See a difference with just monads. It allows to check the correctness of the reasoning and also to check that the laws themselves are correct. Those are the two aspects you want to check. Okay, I start with an example of the kind of equational reasoning we can be doing monad. So first, well, you have to introduce monad, and the monad is just an instance of the monadic interface. So I have a monadic interface corresponding to the exception monad. And this means that M is a monad that satisfies the laws of an exception monad. But it doesn't have to be the exception monad itself. It could just extend. And what I'm going to prove is that the fast product, which is basically a shortcutting product, it's repeating, basically, it's adding all elements in the list S, and it's multiplying elements in the list, and it will stop if there is a 0, and then return 0 in that case, okay? And I want to prove that it's equivalent to just computing the normal product, and as kind of usual when we are doing equational reasoning, there is an intermediate step which is saying, okay, something is going to be equal to, if there is a 0, I fail, otherwise I return the product. And okay, so I start from fast, and I'm going to rewrite, and all the rewrite steps are written in Rock directly. So just first extend the definition. Then we are going to use the universality of fault R. Basically, it's the same thing that I'm going to replace this part by the failed product that I had just defined before. Of course, if I do that, I have to prove that they correspond. Well, here I want this suppress the easy goals, so the base case is trivial, but this I will have to prove, but I will prove on the next slide. So I'm going on, so I've replaced this by failed prod. Going on with the proof, again, expand failed prod. Then I can just do the rewriting to extract the conditional, leave the conditional out. And then I have things that are basically computation inside the model. Catch of fail and catch of red, but those are modally close exactly. So I can just rewrite, which I reach this goal, and here, okay, I have to do a case analysis because it's end of the story. If I do a case analysis, you can recognize that I'm trying to prove that it's equal to product S. So in case it's not in the list, this is trivial. Otherwise, I need to prove it under the hypothesis that 0 is in the list. But I have a lemma that says that okay, if it's 0 in the list, then the product is 0. End of the story. And no, next I need to prove that one. In that case, actually, it's an equality that I want to prove. And I'm going to rewrite on both sides. If I expand everything, I get this kind of goal. And you can see that on both sides, actually, there is this case analysis on whether n is 0 or not. Just do the case analysis. Well, the base case, well, if n is 0, actually, you see that I have failed on both sides. So that's solved. If n is not 0, then here I have the remaining part, which is again an if. And on this side, I have f map of the f, okay? Which, again, I can leave to the if, because f map is just a function. No, from now on, I will be rewriting the right-hand side, so then I get this closed forest map, so that I get this, which is actually exactly the same thing as the left-hand side, so end of the proof. So this is the kind of proof we'll be doing. Of course, so we only allow correct steps, these proofs. But, so in practice there are two sources of errors. Applying laws incorrectly, protecting against that. But using inconsistent laws could be even worse. And when we have many monads and many theories, actually this can become a concern. And there's a well-known example, which was an example in the paper I cited, I gave an hint, that comes in two steps. It comes first from a remark that the probability monad admits the right distributive of bind, okay, which is this law when you don't have to look at the detail. We are here, this is actually a probability between the two possibilities. And the geometry convex monad, which extends the probability monad with non-determinism, which itself is well defined. But that monad does not satisfy this law. So you have to be kind of careful, because it's not because a monad extends another monad that it's going to preserve the law. Those are two different problems. And a funny thing is happening is actually it's possible to create a monad that combine the two and is still satisfy this law, but then there are only degenerate models, so it's not really interesting. Okay, but what it really means is that one has to be extremely careful when building a hierarchy of interfaces. And on the hierarchy, we are building, because the monadic hierarchy here, actually I'm just showing the ones that are cited in the paper. So this is in the GSP paper this time. There are actually many more interfaces in the monadic hierarchy. And the important thing is that it's considered, well, the interfaces, they are both monadic operations and laws. And for every leaf node, you need a concrete monad that instantiates it, and that proves that all the laws are valid. If you have a leaf node, then of course it implies that everything above it will also be consistent. Okay. So why is the hierarchy complex? Well, one reason is that we need all these intermediate nodes to allow subsets of axioms. As I said, some combination may only be valid with less axioms. So it's not because the concrete monad allows more axioms that you could put them in the interface. And the other reason is that we need explicit nodes for all usable combinations. Because contrary to type classes, when you write program with this hierarchy, you cannot use conjunction of constraints. You must use an implicit nodes. And again, this allows to ensure that all use combinations really have a node. You can just write your code supposing that this exists, and at the end of the story, actually, it doesn't exist. And the other point, compared to actually other libraries defined doing this kind of things in Rock, for instance, we use abstract monads rather than concrete ones. Which, well, there are two aspects. One, it avoids to depend on implementation details. I think that's already an important thing. And in our experience also, this means that the code is polymorphic. And if you have that many interfaces, it becomes important because you want to use it at any lower instance also. Another remark actually of all this approach, of all these hierarchies, that closely follows the presentation of algebraic structures in mathematics, which is a pretty natural thing to do. Now, how are we going to build the hierarchy itself? So let's see just a small example with the hierarchy of the non-determinism monad, which combines failure and alternance, multiple possibilities. and we define a monad from a functor. So first you define a mixin using the hierarchy builder, which is a tool for arc framework. A functor is the F-map operation combined with some modes. Technically, in a hierarchy builder, this is just a mixin, so to turn it into a usable node, you have to make it a structure. Then you can build a monad, which has more operation, right join bind, and more laws, like show them. Then we do go on to defining monad fail, monad out. And when you want to define the monad numbet, actually it's defined as inheriting from both from monad fail and monad out. Why the other reason actually you want to have these join nodes is that you might want to add more laws. You're not adding a new operation, but you're adding new laws here. Okay. And okay, so that's how you start your hierarchy. And what happens when you want to extend your hierarchy? Because now you're going to try to prove some things, but it might happen that actually the combination you need is not in the hierarchy yet. And what you can observe is that actually there are two ways to do that. And there's an approach which is I would call interface-driven extension, which is the most common one. It's that, well, the monadic laws are already well streamlined, so you can go look at the paper, and so you're going to add the operation of laws incrementally, depending on the different extension you want to consider. And you need to add, of course, models for each leaf. But there's also another approach, which might be less usual, and that I will describe a bit more detail later, is that, well, you have some concrete monad. You built a monad, but you don't really know its laws. So it's more kind of experimental. So you infer laws from the monad. You can prove them in the monad. You add them to the interface, and then you test them proving example. And if it's not enough, well, just revalue those and do it until you have something usable. And maybe you can try it then to prove that it's a meaningful set of laws. Next, as I said, every time you add a new node, you need a model. And what does it mean? So during extension, so it's newly familiar model for soundness, and also one must register it as an instance for each parent. And there are tools to help that in MonaA. One is that you can use monad transformer to create new concrete monads from existing ones. And the other is that you have a mechanism in hierarchy builder, a mechanism of factories, which allows to simplify the instance registration because it can be clumsy to have to add it for every part. And also, we observe that many models can actually be shared between several interfaces. So, it's short. For instance, if you consider just when you want to create a monad, you don't have to go always through functor. Actually, you have another interface which says, okay, if I have read and join, which identifies some number of laws, then it's a monad. Or maybe more usual for people here, if I have a read and bind, then I have another set of laws that I must satisfy, and then it's a monad with join, etc. That can be used in context. Okay. And next, for monad transformer. For monad transformer, actually, what was done in the joint work with Innova Sauvage is formalizing just kind of modular monad transformers. And in practice, implementing those monad transformers that can be then freely used to combine with existing other existing monads. And what is guaranteed if you do that is the result of monad transformer is going to be a monad that satisfies the interface specific to this monad transformer. Moreover, in some cases, you can also leave the operation from the original monad. For instance, if M is a failure monad, and you apply the state monad transformer, and the result will again be a failure monad with operation, the lifting of the original fail operation. Now I'm examples. First, there's a quick sort example that you can see in the paper, which is based on Moore and Chang's deriving monadic quicksort. And it's interesting because the idea here is that you use non-determinists to give a specification of sort. So it's a new way to give a specification. And usually when you do monadic equational reasoning is just proving that the program is equal to the specification. But here, of course, if we knew non-determinism, the specification is wider than the program. So this cannot be the case that the program is equal to the specification. But what we can do is include the refinement, the notion of refinement in the equality. So if the way is saying that M1 refines M2, program M1 refines M2 is the same as saying that the non-deterministic union of M1 and M2 is equal to M2. That is, it means that M1 is already actually included in M2. And then what do we prove? Well, first define slow sort as just taking all the permutation of a list and then just keeping those which are sorted. And then we can compare quicksort, an imperative version of quicksort with slow sort. In this way, that is, I write the list excess to an array. This is why I need an array plus monad here, starting at position I, and I apply I quicksort to that array. And this is going to be a refinement of doing just the slow sort and writing just the result of the slow sort. Okay. So this is a way to prove things. And if you look at the paper, you realize that actually it's quite tricky to do that. And one of the reasons it's tricky that you need lots of interfaces to do all this result. Okay. Another application is, as I said, well, the type star monad is a monad that was designed actually to represent OCaml stateful computation. That is this model for ML references. And it's used for the translation of OCaml programs. And well, what happened is that we looked around for possible well-known monads representing that, because this looks very similar to the Haskell but actually there is no equational theory for those. There is actually one there was one recently proved, but it's very technical. And what we're doing here to make computation easier, actually, we're using dynamic types. I think it's a bit different from what they are doing. So we need to represent ML types. Actually, since we have dynamic types, store access may fail. So the result is that the monad we are going to build, actually it's the last line here, is applying the state monad transformer to the option monad. The option monad itself is an instance of the same monad. Okay? And in order to make this work, we need this notion of defining what is an ML type and a translation from ML type to Coq type, which will allow us to define our store. A store, well, the cell in the store is just a type and the value of this type, which is defined by this Coq type function. And, but okay, this is the concrete monad, but we need to abstract it. And to abstract it, we first need to abstract the universe. That is, the notion I've given of ML type, actually it's going to depend on the program which you're trying to encode. So we want to be able to change it. And we can define a ML universe of something that's parameter on the definition of the ML types. And then as a function Coq type from ML type to type, type that you know is non-empty. And from this, you can define the ML universe, which packs everything to universe. You have the ML type, the Coq type, and also the fact that ML type is quasi-decided equality. And this gives us actually this interface for the type star monad with operation what new get put, and a large number of laws. Either some can be derived from the array monad, some other are new, because new operation is a new one. And we tested by proving a number of examples. Okay. Okay, I stop. Okay, then I go directly to the conclusion. So monad is an accessible hierarchy of monad interface and models. It allows to do monadic equation reasoning and can be used as a workbench for new monads. That's recent development. We have built a complete Elgot monad for wild maps.
Okay, any questions? Yeah.
And development. I've been using this, I guess, in Rock, and this library is very cool. The question I have is, I suspect there are two kind of different ways to reason about monadic computations, and one, that's what you described, is equational one, which allows to prove refinement, and then also, as I know, there are like works to do like Hoare logic, and then another way is like more kind of F-star, where you reason about monads by generating well weakest preconditions, and then kind of get the formulas and then send them to SMT. So what's your take on like these two different ways to reason about like monadic computations, like the equational one and the one based on weakest preconditions? And yeah.
Well, actually, I do not have much experience on the other one. I'm afraid people using the other one do not have much experience on this side either. So this ends up being difficult to compare. I just got this comment by Kenji Mayar, who's considered to be a specialist of the Dijkstra monads, that in the end you're doing more or less the same thing.
Yeah, it's very similar.
But in my experience, this side requires more preparation. Actually, you should be more careful about.
Okay, yeah, thank you.
Right. Any more questions? Yeah, a very quick one, please.
Yeah, very quick one. Sorry, it's not going to be about the talk, it's just about the very last line. Because I'm a big enthusiast of complete Elgot monads. So what do you mean by modulo by simulation, maybe? You could say briefly. Okay, yeah, thank you.
You're both talking, or what's the?
Yeah, we're both talking.
Okay. Yeah. I hope the microphones will not interfere. Set? We're all set?
Yeah, I think
Okay.
we're all set.
Okay, so the next talk will be given by Arthur and Jona. on almost fair simulations.
Yeah, so we are indeed going to be talking about almost fair simulations, and this is joint work with our PhD supervisor, Bernd Fingbeiner. So what is this talk about? In this talk, we're going to be focusing on proving language inclusion between non-deterministic Büchi automata. And if you do not know what a Büchi automata is, it's simply like a standard finite word automata, except that we are going to run them against infinite words, so infinite sequence of letters. And the semantics is that an infinite word is accepted if a final state is visited infinitely many times. So now you might wonder, why would we bother? And the reason why it matters is that many challenging problems can be modeled in terms of language inclusion between two non-deterministic Büchi automata. And a particularly interesting instance of that is the case of verification of temporal properties under fairness assumptions, and in particular liveness properties under fairness assumptions. Okay, so as a motivating example, we're considering a little concurrent program. It's concurrently executing two loops, one that prints A's and one that prints B's. And the specification that we would like to prove is that globally, eventually A is printed infinitely many times. And if we want to prove that, we'll need to assume that the scheduler is fair. And in particular, we need to make the assumption that the left thread is never starved. And we can model this whole situation using two Büchi automata, one that is essentially encoding the program plus the fairness assumption, and one that is encoding the specification, the liveness specification. And it turns out that the program satisfies the spec if and only if those two automata are language included. And the key takeaway here is that on the left-hand side, we're going to model the fairness assumption as accepting states. So here the Q1 models the fact that the left thread is never starved. And on the right-hand side, on the specification side, accepting state are modeling liveness objectives. So here the R1 state models the fact that we're seeing an A. All right. So now the big question is, how do we actually verify language inclusion? So there exist many algorithmic approaches to do that. For example, there are decision procedures based on automata complementation. But first of all, those are computationally very expensive, and they're essentially restricted to finite state automata. There also exists an alternative option, which are incomplete algorithms based on a notion of fairness-preserving simulation. This is computationally much cheaper, but it's still restricted to finite state, or at least in the literature, it's mostly been studied in the context of algorithmic analysis of finite state systems. And now the question we are asking in the context of this talk is, beyond algorithmic methods that are essentially restricted to finite state, can we also do interactive deductive proofs and exploit this as a foundation to do potentially infinite state systems? To bridge this gap, we're presenting a family of deductive systems to prove language inclusion of NBA, which is based on both known and novel fair simulation techniques. But the key idea here is that those deductive systems are going to support a very intuitive style of incremental proofs via parameterized co-induction. And because we are in a deductive and interactive setting, the cardinality of the state space doesn't matter. So we can support finite and infinite state automata. Cardinality really is not playing a role here. And the whole work has been mechanized in ROC, which both means that we are giving formal foundations. We rigorously argue about the soundness of our fair simulation techniques. And on top of that, because it's mechanized in ROC, we can use our deductive system with the help of the proof assistant.
Inclusion by fair simulations. And before we do that, microphone. Before we do that, I will just talk about what is a simulation formally. So let's imagine we are given two Büchi automata, and we want to prove that two states are similar, or they are in the simulation. And we know that with this smaller equal, so we want to prove that or show that these two are similar. And the definition is exactly that for all outgoing transitions from the left state, we need to find a matching transition for the right state, such that the target states are then again in our simulation. So basically, the executions from S1 are mimicked by the execution from S2, so we're just checking that like the traces are the same. So if you remember the definition of Büchi automata, there was this acceptance condition, and this very plain definition of simulation does not talk about these acceptance condition at all. So this particularly means that the fair executions from S1 are not guaranteed to be also simulated by fair executions from S2. And there's one basic idea to fix that, and it's called direct simulation. And this is by updating our definition a little bit. So I added or we added a condition here, which states that if we are in an accepting state on the left, so on S1, then we also need to be in an accepting state on the right, so S2, which basically means that we need to sync up the existing states, and so therefore we enforce that all fair execution from S1 are also simulated by fair executions from S2. And this still gives us a soundness theorem, so if we can show that they're simulated, then they're language included. Okay, and before I will talk about further simulation.
All right. So Jona explained the trick of direct simulation to get a first soundproof technique for language inclusion. But how do we actually use it in practice in the proof assistant? And what we're going to do is that we're going to package a direct simulation in a little deductive system by manipulating triple with a guarded context. And the idea is that on the right, we have the two states we need to prove to be similar or directly similar. And on the left-hand side, we have a so-called guarded context that contains pairs of states. And the intuition here is that a triple holds means that S1 is directly similar to S2 under the guarded assumption that everything in the context is already directly similar. So before I explain what this guarded thing means and how we are actually operating those triples, we can already claim soundness. So if you can prove such a triple starting from an empty context, you have language inclusion. And the way those contexts are working is as follows. So first of all, to take things out of the context, whenever the box around the context is open, you can always conclude a proof if the states you're looking at are already in the context. So this is how you take things outside of the context and how you conclude a proof. And now the question is, how do we get things inside of the context? And the idea is that whenever you want, you can always accumulate the current states that you're looking at inside of your context. But very importantly, this preserves the guard around the context. And last, whenever the context is open, you can always decide to close it, so it never hurts to close it. So that's all about opening the context, or using what's inside of the context, adding stuff in the context, and closing the context, but the big question is how do you actually open the context? And to do so, there is essentially two ways to make progress. The first one is, so long as the S1 state is not accepting, you can always take a step and open the guard. And another way to make progress is to exploit the fact that the current state you're looking at is accepting in the right. And in that case, you can also take a step and open the context. So let's look at a concrete example. So we take 2 times exactly the same automaton. It's accepting the word AB, 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 AB. We start in Q0 or 0. And the first thing we're going to do is accumulate the initial state in our context. Then we're going to take a computation step. And because we are now in a pair where R1 is accepting, we can use the final rule and go back to Q0, R0. And this time the guard is open. And because Q0, R0 is already in the context, we are done by cycle. So very simple intuition.
Okay, so back to our direct simulation. So unfortunately, direct simulation is still a little bit too strong. So if we take these two automata in our example, it's almost the same, but we change the accepting state here from R0 to R1. So there's still language included because both automata still only accept the word AB, AB, AB. But actually Q0 and R0 are not directly simulated anymore because the accepting states doesn't match up exactly. A way to circumvent that is so-called delay simulation. So delay simulation has this intuitive idea that we delay the time we need to see the second accepting state. So after we see an accepting state on the left, so F1 accepting state, we can finally delay, so do finally many steps until we see a subsequent listen to an accepting state on the right. And even with this more weaker notion, this is still sound for language inclusion. Let's now look at how this would look in our deductive system. So this general idea, so we see an accepting state on the left, and then we need to check finally many step until we are allowed, until we see a final state on the right. We do this with 2 kinds of triples, so we have our left triplet and our right triplets. And the idea is now exactly that. So we have the left triplets where we start and we stay in there until we see a final state. Then we notice that we see a final state on the left, and then we switch over to the right relation where we then stay in step until we see a visit to an accepting state on the right. So we wait there, and then we go back to the left relation, and it starts again. So they play like together. Okay, and with this, we again get soundness. So if these 2 states are simulated, then they are also language included. Okay, how does this look exactly? So let's look at the rules. So we first look at the left rules. So when we search for an accepting state on the left, so we still have the same rule which says as long as we do not see an accepting state, we can just go on and open the context. And then we have the other rule that if we then see an accepting state, we need to switch from the left relation to the right relation. And then we have the right rules. So first, as long as we don't see an accepting state, we can just step. But importantly here, the context stays closed because this is just like a helping thing where we track finitely many delays. And then this is the rule that helps us then to open the box again. So if we see then a finite state on the right, then we can step and open the context and also get back to the left relation here from the right. Okay, let's look at an example. So I took the example from before. So these are our accepting states. And we start from Q0 and R0, and we start in the left relation. So first, we want to accumulate these states. So remember that you've already seen them. Then, because Q0 is accepting, we need to track that and need to switch to the right relation, and therefore switch to the right relation, but this is not final. R0 is not final, so we do a step. So we switch to the right relation and then do a step, as R0 was not final. And then, afterwards, we are in Q1 and R1 is now final, so we can use our final rule to then step again and open the context, and then we are back at Q0, R0, and these we all have already seen, so we can conclude with our cycle rule. Okay, unfortunately, delay simulation is still too strong, so if you look at the following example, both automata just accept the empty language because they just loop indefinitely at a non-accepting state. But the left automaton has some random accepting state in the beginning, and therefore Q0 and R0 are not delay simulated anymore because this accepting state here forces us to go into the right relation, but then we never see an accepting state here, so we kind of are stuck in there.
So this example seems a little bit artificial because actually the languages are empty, so we could as well have removed the accepting state here. But it turns out that this is not always the case. So this problem can actually occur in practice on non-trivial Bucci automata. So for example, here we have an example where we have some sort of a scheduled task where we start in some state Q0, then we might schedule a task, then there is an initialization phase, we work for some amount of time, and then at some point we are done, and we have a fairness condition that guarantees that we are doing this infinitely many times. And the specification that we care about is to show that we terminate the task at least once. And it turns out that actually we can also not prove this by delay simulation, and the reason is simply that once we are getting to Q1, this generates an obligation to have a visit to R1, but the left-hand automaton can stay stuck in Q2 forever doing some work, and we have no way to get out of that. So to weaken delay simulation, we propose a repeated delay simulation. And the idea is that we still enable delay, like in delay simulation, but we additionally enable to skip finitely many visits to F1. So we're going to generate less obligations to visit F2 states. So this is still sound for language inclusion. And the way we're going to implement a deductive system for this is by adding a new kind of triple. So we still have the left and right triples that are inherited from delay simulation, but on top of that, we also have a new kind of weighting triples. And the intuition is still the same for the left triples. We are tracking visits to F1. Upon visits to F1, we are forced to switch to the right relation, which forces us to eventually get to an F2 state. But this time, instead of circling back to L, we are actually going to those weighting triples, which enable to first skip finitely many visits to F1 before we commit again to tracking F1 states. So this is still sound for language inclusion, and in particular, we get to start from a weighting triple, so we can wait in the beginning as well. All right, so how does it look like? We need to update slightly our write rules. So we still have the delay rule, so we preserve the ability to delay as in delay simulation. But the twist is that now, whenever we see an F2 state, instead of immediately going to L, we can go to W and wait for some time. So skip some obligations temporarily. And so the waiting rules are as follows. We can always unconditionally take a step so long as we're in wait. But in addition, whenever we want, we can actually open the context so long as we commit to start tracking F1 states again. So to see how it works in practice, let's look at this example that we discussed before. So we start in Q0, R0. And the key idea here is that we are going to wait to skip through the Q1 state and not generate an obligation. So we use the rule wait 2 times, and we get to Q2. But very importantly, the visit to Q1 did not generate any obligation. And then from this point on, we can use accumulate to store Q2 and R0 in the context, and the rest of the proof is essentially straightforward. So I'm not going to give the full technical details. All right, so as a summary, we started from a direct simulation and presented a deductive system associated with it and proved that it's sound for a language inclusion. We also discussed that direct simulation is way too strong in practice, and we discussed how delay simulation is much weaker and can still be presented as a very intuitive deductive system. And finally, we presented an even weaker and new notion of fairness-preserving simulation called repeated delay simulation, and it still preserved this nice deductive system. So all the results and all the deductive systems have been mechanized in ROC, so feel free to have a look at the ROC development online. And as a conclusion, maybe a few words on potential future work. So even though the repeated delay simulation is significantly weaker than delay and direct simulation, it's still too strong. There are examples that are not covered. But there exist in the literature some weaker notions of fairness-preserving simulation. Unfortunately, those require some very sophisticated co-inductive, inductive, co-inductive reasoning. So there is a lot of work to be done here, but it's not obvious that we can still have those nice deductive systems to reason about them. Another line of work would be to look at other fairness conditions than Bucci. So in the context of this talk, we talked about Bucci automata, but actually there are other kind of infinite words automata with slightly different acceptance conditions. It would be very interesting to look at fairness-preserving simulation for those as well. And last, in this talk, the deductive system we looked at are very low level. We reason directly against models of programs and explicit states. It would be much nicer to combine this with a program logic, for example, in a style of similaris. Yeah. So that's it. If you have questions, we are happy to answer them.
Okay, any questions? Maybe I start then. So, I mean, there are very fancy forms of simulations like up-to, right? Can you reflect this in your system, up-to techniques?
That's a very good question. Yes, it's possible, but there are things you need to be a little bit careful about because, so one thing that I've been thinking about recently is whether this supports up-to context. And I think it kind of depends. Because if your context introduce some new some new obligations, so some new F1 states, then it's not clear that you can reason up to context. So I think you need to be a little bit careful, but there are other up to techniques that should work. But yeah, this is a very good remark. Short answer is probably, but I need to investigate more.
Right. And maybe on a related note, so personally, before I learned about fair simulations, I learned about Ramsey-based inclusion checking techniques for Bucci automata. Do you know if this is somehow related to the simulation-based stuff, and whether you can reflect this also in a proof system? That would be quite cool.
Do you know?
Yeah.
No, I have no idea.
Yeah. Yeah, I think it goes back to Clemente and people like this, but okay, would be quite interesting to see it. Okay, any more questions? Yeah.
Hi, thanks for the talk. I feel like I got from the summary a pretty clear idea of why you can't just rely on your standard old simulation techniques. I don't have as good an idea of intuitively how I should understand the context being open or closed. I was wondering if you might be able to patch that in.
Yes. So the opening and closing the context is just this idea of parameterized co-induction. It's actually not from us. It's a standard idea now in the field of interactive proofs by co-induction. It's just here to model the fact that actually we had a talk about co-induction earlier that was mentioning this difficulty of context, of guards. Like you need to have when you're using a co-induction hypothesis, you need to make sure that it's guarded. And this is exactly what this corresponds to the idea that you cannot directly use your co-induction hypothesis before you actually made some progress. So the guard around the context is just here to make sure that you are actually making some progress towards your goal before you're exploiting the co-induction hypothesis.
Should I understand it as sort of like a dual of a termination check almost, or? Okay. Anyway, sorry, I wasn't here earlier.
I'm not so
in
sure
the
about
session.
that. It's more like it's one way to understand this guardedness condition in standard co-inductive proofs.
Okay, thanks.
Any more questions? If not, then thanks to both of you again.
Connect the computer. Yeah.
Good. So the last talk in this session will be about, well, my personal favorite topic right these days, higher order mathematical operational semantics, and Sergey is going to talk about how to make big steps in this setting.
Yeah. Hello, everyone. Do you hear me well? Yes? Okay, thank you. Thank you, everyone, for coming. Indeed, this is going to be a talk about big steps in higher order mathematical operational semantics. More precisely about an abstract connection between big step and small step. This is joint work with Puya Partov from the University of Birmingham and Stelios Stampas from the University of Southern Denmark. So, and I would like to give a little bit of context to this work. So it's basically part of a bigger effort which started in 2023. Where we introduced a notion of a higher order mathematical operational semantics, which builds on a previously known notion of just an ordinary mathematical operational semantics, which can now be called first order, which has been introduced in a seminal paper by Turin and Plotkin. So we extended that work by a certain ability to model higher order languages. And so this has sort of opened a door for a certain meta reasoning about operational semantics within a category. So, and subsequently, we developed this approach in a range of papers. Last of those being, I mean, except this present one, also the last one in this list, which has been presented by Henning today. So if you have been to the morning session, you might notice that this is related. So in a nutshell, so what is it all about? Yeah, very conceptually, we are aiming at making operational semantics more mathematical. So, and this was also the original motivation by Turin and Plotkin. The main idea here is like to consider an operational semantic as some sort of input, like a set of rules, and using abstract methods, using the language of category theory to first obtain a categorical abstraction induced by these rules, and from those devise method and properties. So just as an example of methods, these are some sort of abstract notions of logical relations or abstract house method, other things. And what I mean by properties is some sort of compositionality, safety, adequacy. And most of the papers in this list from the previous slides, they are addressing really complicated things like proving congruence of the contextual equivalence. So in this concrete work, the issue is much simpler. It's just equivalence of big step and small step, but it's also an illustration of this general idea of obtaining something general through abstraction. So, and a nice side effect of this approach is that since it's modeled categorically, a side effect of this, it also tends to be translatable into some sort of functional implementation in functional languages or in proof assistance. And this is exactly the case for this work. Indeed, the paper comes with an artifact which implements most of the things that I will be talking about. So I could actually have given this talk completely differently, just like some kind of implementation talks and talk about type classes and functions and so on. But I choose to present it using the more versatile language of category theory. So I will explain you the problem by example. Yeah, first I would like to show you this concrete example, which we like, in particular because it's very nice to illustrate derivations and like operational semantic derivations of a higher order language. So some of you might be familiar with the combinatorial logic. It's a certain flavor of combinatorial logic SKI, where we have three combinators that correspond to certain lambda expressions. And this language of combinator being so concise, still computation equivalent to lambda calculus. Yeah, so we have a couple of non-standard features here, and that, in particular, that certain combinators have variance. So this K combinator, which is standard, stands for constant. But we also have K prime, and this is because the K is binary, but we would like to model the situation when it consumes one argument, and then it's in the position to consume another argument. So when this happens, we have this intermediate combinator K prime waiting for it. Another non-standard feature is that these labels, so labels consume, well, indicate an argument will be consumed at this stage. So it's a mild variation of combinatorial logic, and well, one can see easily that you can model transitions of the original combinatorial logic in this way and the other way around. So this language is very simple, it's purely algebraic, and it's higher order still. And it's well suited for presentations because of its simplicity. So of course, the problem is here, you might wonder, well, okay, what's about lambda calculus? And yeah, that's still being just as powerful as not lambda calculus. And lambda calculus just adds some layer of technicality about modeling name binders. And so that's why it's not optimal for presenting the main idea here, but bear with me. If I have time, there is a slide in the end about it. Yeah, so we can define big step semantics for this little calculus. It would look roughly like this. So we need a notion of value. We can introduce it by a grammar. So a value will be something that has a constructor on top of it. And we have the evaluation relation, which relates a program to a value. It's supposed to be derivable in this very simple system, which would mimic the corresponding big step semantics in simply time lambda calculus. And okay, so what the rest of the talk is about is this equivalence theorem, which basically states that small step semantics is equivalent to big step semantics in this particular sense. And so the question is, can we do this abstractly on the meta level, ranging over all possible rules? And a sub-question of this, can we make sense of it? Because before proving it, we need to interpret all these components in this equivalence. So yeah, this is what the rest of the talk will about. Just to avoid confusion, I will reiterate it here. And let me first explain this general notion of abstract higher order GSS. This is formulated using very rudimentary parts of the category theory. So I will not need more than the notion of a functor, a notion of natural transformation, algebra, and a monad. I don't even need all algebra. Mostly what I need is the algebra of terms. So I will need to fix some kind of signature, which is a functor, and terms in the signature are free algebras with respect to a given set of variables. So, and in Haskell, for example, it would be an inductive type. And we will use this notation for terms without variables. So we also will need monads, natural transformations. You can just think about them as polymorphic functions if you're not familiar with natural transformations. So another slightly less familiar notion from category theory is really the final one. That's a notion of dinaturality. So dinaturality is some generalization of naturality. It works, well, it's invented as a generalization for functors of mixed variance. So it's a functor with two components. You can think about them like input and output. And so like saying that they are natural in some sense with respect to this argument amounts to commutativity of this diagram. And the prototypical example of such dinational transformation is the evaluation morphism. So there are like two occurrences of X, input and output, and to say that we are sort of natural in them, but technically speaking dinatural, we need to make sure this diagram commutes. And this is like a prototypical example. By composing functors based on this example, we can generate more dinational transformations. Okay, that's that. And then, so what is a higher order abstract GSS? Like I said, the idea comes to this paper towards a mathematical operational semantic Turing power, Turing-Plotkin, sorry. And in our case, we generalize it. I highlight in green what is added on top of it. So we fix a signature in a standard way. Then we define a functor, which is called a behavior functor, and it models the transitions in the operational semantics. So what we add is this contravariant part of the functor, which correspond to labels on the transitions. And also, the main ingredient is this family of functors, which is natural in Y, just like in the sense of this paper, but it's also dinatural in X. So, and for combinatorial logic, how this is instantiated, so we take as a category the category of sets. As a signature, we just take the algebraic signature of the combinators, and as the behavior, so this is precisely a direct product of two relations. One is unlabeled arrows, and one is labeled arrows. And now you see why we need the this exponent, because we consume an input which is comes from the label of the arrow, and this input corresponds to this X here. And raw, so this is the most complex part. It's this natural dinatural transformation, which is induced by the operational semantic rule. I will sketch very briefly how this is how this works. So, for example, if we take these two rules from the semantics of combinatorial logic, they will generate this raw of this form. So now I expanded the functor, and so this green is, for example, this corresponds to the original term that we are reducing. But in addition, we can use on the right-hand side, at the bottom of the rule, the successor of one of the subterms. And these corresponds, for example, to these positions and this natural transformation. Or if one of the premises transits via a labeled arrow, this corresponds to this position, and this also can be used. So if you spend enough time on this, you might see how we can transform rules to this natural denatural transformations. And this is the first step in this abstraction process. So we starting with the set of operational semantic rules. We can define an abstract HOGSOS. And by generalities, we can, for every such HOGSOS, derive what is called operational model, which abstracts derivable transitions for every term. So for every term, we can find a successor, which is the derivable one in this deductive system for operational semantics. And this is defined abstractly using the fact that the algebra of term is initial. So for combinatoric logic, this operational model, well, it does what's expected. It has two cases. Either a term has a silent transition to a successor, or it has a label transition. And that corresponds to two parts of the coproduct in the functor. Okay, now back to the issue. So this was all known, and our new challenge is how to model a big step semantics and how to connect it to small step semantics. If we look at the big step semantics of the combinatorial logic, one can notice that we cannot just frivolously inspect behaviors of the operands. So if I want to evaluate a composition with respect to lazy semantics, it would make a difference if I check what T evaluates to or not. Because if T is a divergent term, then the left-hand side might converge, while the right will always diverge. So this means that on the level of signature, I need to separate those arguments which are strict and those which are lazy. Otherwise, I will never be able to distinguish these two cases. So this is the first change. In order to basically to make sense of this equivalence claim, another thing is that this equivalence claim also contains a transitive closure of the small step semantics. And in order to model it, we need to define it as a least fixed point of the one-step transition. And to do this, we also need to refine the behavior functor. It must include a monad. I mean, this is our solution, which supports solutions of the least fixed point equations. So we assume that the signature decomposes into a part for values and part for the computation. We assume a monad, and in the end we arrive at this refined version of the abstract HOGSOS, which we call separated. So it now has a value part, it has a computation part, and it refines properly this more general abstract notion of HOGSOS. I'm not showing you how it converts back to it, but it does. It's relatively easy to see. Similarly, we can define operational model, but now it will have two parts. So values will have their part of the operational model, computation will have their part of the operational model, and we also can define this multi-step semantics thanks to the fact that the monad supports fixed points. And since we introduce a monad, we also can use it not just for solving equations, but we can also model computational effects. Because if we take the monad to be the parsed monad, for example, we can also capture non-deterministic semantics, just like by adding this kind of rules. And then, the last ingredient that we need is the notion of this big step semantics in this equivalence statement. And so it also captured by a natural transformation. So intuitively, this format of natural transformation corresponds syntactically to these rules. So we want to evaluate a term, and we can evaluate strict arguments of the term and then pass the result to some other term, evaluate it, and that result of evaluation is the net result of evaluation of the original term. Right, and okay, so we nearly done with proving the statement. We made sense of all these ingredients. So we defined multi-step transition, we defined what is a value, we defined what is a big step derivation, but is this equivalence true? Actually, it's not necessarily true, because despite these conditions that we imposed, well, it's very easy to break this equivalence just by introducing rules like this rightmost one, the first one. So we make one step of the argument at the top, but then we change the principal symbol at the bottom. And yeah, so this breaks this kind of equivalence and can be exploited easily to break the equivalence you want. So a solution to this is kind of ban this sort of rules and introduce this condition we call strong separation condition, which I describe on the slide. And it's kind of restrictive, but it's very sensible from practical perspective. This is well-behavedness condition one expects from the operational semantics. So this kind of situation is not possible. If you're reducing some argument under a function, that function shouldn't change. And the main result now, if we start with a separated HOGSOS, which is additionally strongly separated, and there's a categorical formulation of this in the paper, I just didn't show it. So then a small step semantics uses big step semantics, and they equivalent in the sense that operational models agree. So I guess I don't have time for this. What I was talking about was the lazy version of lambda calculus. There are more examples in the papers. This is particularly interesting one, but I don't have time for this. So if you change the strategy to call by value, something interesting is happening, but in the end it's also covered. So also languages with binders, we can also make lambda calculus, also one of the examples, with a little bit of additional work. So if we look at this standard rules for small step semantic and big step semantics, they are not directly fitting the format we need, because secretly the rule for lambda abstraction alludes to the substitution. And substitution actually is yet another kind of behavior which is implicit in the standard treatment of lambda calculus. But if you want to do this functorially, then you need to make it explicit. This amounts to modifying the value part of the HOGSOS law by adding this ingredient, which is certain object of substitution action. You need to select the category as a category of certain pre-sheaves. This has been done for the syntax by Fiore and Plotkin in this paper, so we can just capitalize on this work to change this particular part of this framework. Right, conclusions. We have defined the abstract notion of small step and big step semantics, proved the equivalence, and last but not least, formalize this all in Haskell. The paper comes with an artifact with a barcode leading to it. I really suggest you play with it a little bit. It's very simple. but it contains like an implementation of it with a bunch of Haskell classes and with examples that I mentioned and a bit more. So here are some further work. Maybe what I mentioned here, which is I found particularly relevant, is so this question of relating the mathematical theory and implementation. So this implementation currently we have is very close to the mathematical theory that I present. Because if the signature is algebraic, then you can model it as an inductive type in Haskell. It's not exactly the same, but it pretty much captures the spirit, and it's essentially the same. But if you have like binders in your signature, the mathematical theory, again, it's more complicated, but it's clear. But I'm curious what it corresponds to. I was trying to find some ways to implement it in Haskell. I found the so-called nominal library in Haskell, but couldn't really make use of it. So given that there are lots of experts here in Haskell and functional programming, I would be very delighted if someone reaches out and suggests me a way to implement this kind of meta framework in Haskell in a proper way, so that with the proper name handling and making things that must be a functor, here the functor, and so on. So thank you. This is it.
Any questions? Yeah.
Just a quick question. I missed the part that when you mentioned if there are non-determinism in the operational rules, how does that manifest in the operational model after the translation?
These are the rules which one can use for non-determinism. And so here in the operational model, I mean, it's manifested as expected. So for a term, I will have a set of successors. So because this T is a power set.
So if you translate this into a Haskell program, how does that run?
Well, I mean, you do it Haskell way. You replace power set by lists.
Oh, okay, thank you.
Hi, I'm Jens Pausberg from UCLA. Very enjoyable. I have a question. So the way I see your conclusion is that under certain conditions, you can prove that multi-step semantics does the same as big step semantics.
Exactly.
Those conditions, are they checkable? Is that like asking whether this set of rules I give you satisfies the condition of your theorem? Is that something we can check with an algorithm?
Yeah. So there are like 2 degrees of abstraction.
Yeah.
There is like an abstract condition on the in terms of natural transformations, and there is a concrete instance like if they come from these rules, just look at these rules and inspect them, and you will know yes or no.
And so both of these are quite checkable.
Yeah, well, the first one is slightly less checkable and it's also more general because you can have complicated categories and functors without obvious syntactic presentation, something like that. So it's more general, but it's less easy to check.
Right. So if there's any more question, if not, then let's thank Sergey and all speakers again. If I'm not mistaken, there's a poster session, right? Right.